So today we will be studying about the relation between electric potential and electric field charge. Okay. So here basically how we can start is that let's say that you are having source charge. Okay. Let's say that Q is my source charge. So E is my source charge. Okay. Now, since he is the source charge, so he'll be generating a certain electric field, and due to that electric field generated by this Q charge, you will have different potential values at different points, right? So what we will do, we will be considering certain points here. Let's say that you are having a point here. Okay. Let's name it A, capital A. And let's say the potential at this particular point, let us consider it as V suffix A, or let's say only V. Okay, if you are considering V suffix A, we'll just consider it only V. So the potential at A is V here. Okay. And let us consider another point B, somewhere here. And the potential at this particular point, let's just consider that it is V plus dV. And we will assume that the distance between this A and B is as dr. Okay, so you are having a source charge Q who is generating a certain electric field, radially outward electric field, and due to that electric field you will have different potential values at different points. Okay, so considering those points as A and B with potential V at point A and V plus dV at point B, and the separation between B, A, B, and A and B, let's just consider it as dr. So these are our assumptions. So what we will do now, we will be considering a test charge. Okay, Q naught. He will be my test charge. Test charge. And when we say test charge, so we understand that this charge Q naught is going to perform certain work. Now what we will do, we will allow this charge Q naught to move from this point A to point B. Okay, so we have electric field in this direction. So we are having electric field in this direction. Okay, so this is my electric field E. So and the charge is moving opposite or against this electric field E. That means when this charge Q naught is moving against this electric field E, so we understand that this charge Q naught is doing some work against this electric field E. Okay, so considering how much amount of work this Q naught is doing, so based on that work done only, we'll be finding out the relation between electric potential and electric field. Okay, so we will just note it down what are the assumptions we had made. We had made that at point A and B, okay, potential are capital V and capital V plus dV. These are the potential, and A and B are separated by a distance dr. So work done. So therefore, we'll be finding out work done in two different ways. So first, we will find out work done the way we have studied in class 11. Okay, work done by Q naught. Okay, so Q naught is moving in moving from A to B. Okay, so we have studied it as the dot product of force and displacement. This is how we have studied. So this is my displacement dr and this is my force. Okay, remember in this case our force is nothing but QE. Okay, so in this case our force means electric field E is generated by this source charge Q, and this Q naught charge is going to face or feel this electric field. So because of which, in place of this Q, you will be having this Q naught charge. Okay, because he is actually feeling this electric field E. Okay, but now as you can see clearly that displacement dr or the charge who is moving from A to B is completely in opposite direction, right? Is in opposite direction as compared to the electric field E. Okay, it makes an angle 180 degrees, because of which we have a negative sign here. So directly we represent that this multiplication of f dr, the negative sign. Okay, so this is my work done. This is one way. So we can give this equation 1. Another way of finding out work done will be, with respect to the potential difference between A and B. So work done by Q naught. Okay, so how we will do that? So we have studied that potential difference is nothing but work per unit charge. So when we find work done, it's again nothing but multiplication of that charge Q naught with the potential difference between A and B. All right. Now the potential difference between A and B is nothing but dV. So we will directly write it down it as Q naught dV. So this is the amount of work done. Work done by whom? By the charge Q naught. All right. So again, this dW, we write it as Q naught dV. You can give this as equation 2. So we have the expressions of work done in two different ways, and the last final step will be we will be just making this two work done equal to each other. So from 1 and 2, right? So from 1 and 2, when we just make these two equations equal to each other, so we get minus f dr is equals to Q naught dV. Okay, so when you replace this f value, which is nothing but Q naught E, you get Q naught E dr and Q naught dV. So Q naught gets cancelled. So you have this relation as E equals to minus dV by dr. Okay, so this is the relation between electric field and the electric potential. Now you see that you are having a negative sign there. Okay, so how we are going to understand what is this negative sign signifying? Look at this diagram. So as you can see here in this, that when electric field is actually moving in this direction, you are moving actually in such a region where potential difference, potential at every point is actually decreasing. right? So electric field, when it moves radially outward, that means it moves in a direction where potential decreases, right? Because potential value will be more when those points are considered more close to your source charge. Okay, so you can make this as a point. The negative sign signifies that uh, electric field is moving towards a decreasing electric potential, region. Okay, so this is what your negative sign states, right? And this factor dV by dr is known as potential gradient. This is known as potential gradient. Okay, so that means what it means. It's nothing but rate of change of potential. Let's say V. We'll keep it as V. Rate of change of potential with respect to distance, that is R. So that means if you see this diagram, the more you move away from your source charge, okay, the more the potential value changes. And potential value is a function of the distance, right? So this is what this dV by dr is actually telling me, okay, where R is my independent quantity and V is dependent, and he is depending on the distance R. Okay, so this equation is very important with respect to the relation between this potential and electric field. So with this, you can find out if suppose in any question electric field is mentioned to you, and you are asked how to find the potential value, so you can easily find out that V potential. Okay. Okay. So if you see here, so here in our question it is asked that you are having two parallel plates, and both these parallel plates are separated by 5 centimeters, and they are having a potential difference of 60 volt. Okay, you have to find your electric field intensity between the plates. Sorry. So this is, let's say these are the two plates, and the distance between them is, let's say, just 5 centimeters, and potential difference, let's say, is 60 volt. So here your dV value is 60, and your dr value is 5 centimeters. If you bring it in SI units, you get around 5 to the minus 2 meter. Okay. If you use this relation equals to minus dV by dr. Okay. So we just replace this value C by 5, so you get around 12. 5 into 10 to the power minus 2. You get around 1200 volt meter inverse. So this is the amount of, or you can say the electric field intensity between the plates. All right. Now, as you can see here, there is a negative sign. This negative sign indicates that electric field is directed. Okay, electric field is directed in the decreasing electric potential region. Okay. The electric field will be directed towards the region where electric potential is in decreasing process. Okay, the more you move away from the source charge, and the more the value of electric potential decreases. Okay, this is what it means. This is what this negative sign refers to. So here we will be studying about equipotential surface. Before going into understanding equipotential surface, we will take some few assumptions, and then we will understand the exact definition what it means. So first, what we will do, we will consider a very small charge, okay, Q. We use my positive charge, and I will assume a point, let's say somewhere here. Now, since he is positively charged, so he is going to generate certain electric field, in this region at the vicinity of this charge. Now, due to the electric field generated, you will have certain potential, and the more you move away from this charge, the more the potential value decreases. Okay, we have discussed all these things in the earlier classes. So right now, what we will do, we will assume that this Q is located somewhere in this region, and we consider another point, let's say P. And we know that due to this Q charge, we will have certain potential value, and that potential is nothing but KQ by R. What is that R? This R is the distance from this Q to point A. Okay. So now what we will do, if we draw a sphere, okay, if we draw a sphere with this sphere, with this radius R, okay, let's say that this is the sphere with radius R, that means this Q is at the center of the sphere. So if I assume various points over this sphere, let's say this is point B, let's say this is point C, D, and all these points will be at same distance from this Q. That means will be at distance R from this Q. Okay. So obviously, the potential which we have observed at point A, which is nothing but KQ by R, that same potential will be validated at this point also, which is again, sorry, it is going to be small q. Okay. So that same potential we will see here also, which is again KQ by R. Here also we will see same potential KQ by R, and here also we will see the same potential KQ by R. Okay, this is going to be small q. Okay, so that means this sphere at every point you are having same potential. So this is what equipotential surface means. That means this sphere which I have drawn, this is an example of equipotential surface. If I want to define what is that, okay, so any surface, okay, over which the electric potential remains same. Okay, any surface over which the electric potential remains same, so that surface is known as equipotential surface. Is known as equipotential surface. Okay.
We have also discussed one more example in earlier topic. We had calculated potential due to an electric dipole. When we say electric dipole, so we understand that you will be having a minus q charge and you will be having a plus q charge. Okay, and the distance between these two, it is going to be let's say twice a. So if I and you will have a certain point of origin O here. So if I draw a line, okay, which is passing through this point O, okay. So if you calculate, if you find out the potential value at every point, let's say that if you want to if you want to calculate the potential at this point, let's say A, okay, the value of potential A at A due to this minus Q and due to this plus Q. So you will find that potential value is 0 here. Okay. Then again, if you assume a few more points, let's say you assume point B here, you assume point C here, you assume point D here. So at every point you will have 0 potential. So that means you are having equal potential value, even though the value is 0. So at every point you are having same value. So this is also one example of equipotential surface. Okay. So, but there are various properties, which is related to equipotential surface. So we will study those properties. So these are the properties of equipotential surface. Now our very first point which comes across is this point. Like there is no work done in moving a test charge over an equipotential surface. Okay, so you will not have any work there if you allow any charge to move over an equipotential surface. So let's just understand what happens here. Okay, so let's just assume that you are having an equipotential surface. This is my any surface, and since this is equipotential, okay, this is my equipotential surface. Since it is equipotential, the potential value will be same at every point. So let's just assume that you are having 2 points, A and B. So the potential at A is equals to potential at B, and let's just assume that that potential is V here. Okay. Now what you do, you consider a test charge here. This is my test charge, and he is allowed to move from point B to point A. Okay, so let's just recall what we have assumed. We had assumed that this is my equipotential surface over which your potential value is same, equal. Let's just assume that it is V. And over this equipotential surface, we had assumed 2 points, A and B. Okay, and now what we do, we are allowing a test charge. Who is my test charge? This Q naught. We are allowing this test charge to move from B to point A. This is what we're doing. Okay. So obviously, so we understand now that if this particle is moving from one point to another, he is going to do certain work there. So we'll find out that what is the amount of work done by this charge Q naught. So work done by Q naught in moving from B to A. This is the amount of work done, and what will be that? This multiplication of the test charge with the potential difference, VB minus VA. Remember, we have studied, what is potential difference. The potential difference is nothing but work done per unit charge. So now we need to find a work done value. So you just multiply this charge value Q naught with the potential difference. And since this is equipotential surface, so you will have no potential difference because at both the points you are having same potential. So this part turns out to be 0. So you get no work for such a case. That is why this is one of the most very important point. If you allow your test charge, and if the test charge is moved from one point to another, will there be any work done by that charge Q naught? So my answer will be no. So there is no work done, work performed by the charge. Now this is my first point, and this is very important because from board point of view, this is actually very important. They ask a very 2 marks question. No work is done. They will present the question in such a manner that no work is done in moving a test charge. Full stop. Give reason. So you have to give this reason. You have to consider an equipotential surface, and you have to show step by step that how you don't find any work for such case. Okay. This is our second point. Now here, what did we say? The electric field is always normal to my equipotential surface at every point. Okay. So what we do here, again let's just assume that you are having a charge Q, and from this Q to this point, let us consider that this point is A, okay, and this distance is R. To this point A, we want to know the potential value. Okay, so we know that how much it is, K Q by R. This is the amount of potential at point A. Now, considering this radius R, so what we do, we draw a sphere. Okay. We draw a sphere, and this Q, we assume that it is at the center. Okay. This is that sphere, and this Q is at the center of this sphere, which is at this, and this point A is the distance R from this Q. Okay. So if I assume different points, let's say somewhere here, let's say somewhere here, let's say somewhere here. So at every point you will have same potential. So hence this is nothing but an equipotential surface. Okay, so this is what we have seen here. Now, if I want to know the direction of electric field, because this is my plus Q, which is located in a certain region, and he is behaving like a source, obviously he is going to generate a certain electric field. So we have studied in chapter 1 that what should be the direction of such positive charge. So we have understood. So you will always have radially outward electric field. Okay. You are having a radially outward electric field in all the directions. As you can see clearly that this electric field lines E is always making a 90-degree with this equipotential surface. That means this electric field line is normal to equipotential surface. Okay, so this is my second property, that for any charge, your field line will be normal to my equipotential surface. This is my second property. Now my question is that if this field line, if I assume that it is not at normal position, if I assume that this field line is making certain angle with the surface, so what will happen in that case? Okay, so let's just assume that this is my surface, equipotential surface, and let's just make that this electric field is now not normal position. Instead, he is inclined at certain angle. Okay. Now, since he is inclined at certain angle, we had studied in class 11 how resolve the vector. So that same process we will perform here. What we will do, we are going to resolve this electric field E, since he's inclined at a certain angle. So if you resolve this, so you will have one component in this direction, and you will have another component in this direction, right? So this is my normal component, and this is my tangential component. Tangential to what? Tangential to equipotential surface. Equipotential surface. And we will get these two components only if you assume that you are having a certain electric field component which is not normal to my surface, equipotential surface. Instead, he is at certain angle with my equipotential surface. Okay. So in such case, what will happen? So now what you see is that you are having a component which is tangential to the surface. You are having a component. Let's say that you are. Let's just assume that this component is EX, and let's just assume that this component is EY. So you are having two components there. Now due to this electric field EX. Okay. Now if I take a test charge now. If I take a test charge Q0, and if I allow him to move from one point to another, okay, then what will happen? That he will have a work done which is against this electric field, right? So he is going to perform a work which is against this electric field. So that means we are going to get a work done value. Okay. Now since we had stated in point 1, first property, that when a test charge is moving over any equipotential surface, we don't find a work done value. Why? Because the potential difference for every point is 0. Between 2 points is 0. That's why your work done value is also 0. So in simple terms, there is no work done performed by any charge moving from one point to another. This is what we have seen in first property. But if you look into this case, he is contradicting our first property. Okay, and what is that? Because in this case, you are having a component electric field EX, and if the test charge is again moved over the surface, you are going to have a work done which is against this electric field, which is not possible. Okay, so that is why your electric field line, they are always normal to my equipotential surface at every point. Okay, so this is our second property. Now let's just see what is our third property. Okay, so as you can see here, this is our third property, and what it states that equipotential surface are closer together, close together in the region of strong field, and farther apart in the region of weak field. Now let's just understand, what is this point is trying to say. Now we have this relation E is equals to minus dV by dr. This is the relation between electric field intensity and electric potential. Now if you see the relation between electric field E and this dr. Okay. Now what is this dr and what is this dV? dV is the potential difference between two regions. Okay. If I assume that this is one plane surface and this is another plane surface, okay, and you are having a certain potential difference between these two, okay, dV, and you are having a certain distance between these two, let's say dr. let's say dr. This is the distance between these two planes. We give some certain name here, like this is A, this is B, and let's say that you are having a certain electric field in between this plane. That electric field is E. So this should be the relation between this electric field E and the potential, electric potential. Okay. So from this relation, we understand this electric field E is inversely proportional to that distance dr, right? So what we can make from here is that if you assume that two surfaces, and if you make those two surfaces very close to each other, okay, so when you say very close to each other, that means the distance between those two planes, that will be very small. So in such regions, you will have a very strong electric field. Okay, so let's just say that this is any surface, this is an equipotential surface. Okay, this is an equipotential surface, equipotential surface. Okay, let's just say that the potential for this plane A is BA. So that means at every point over this plane, you will have this same potential, which is BA. And the potential for this plane B, let's just say that is BB. Okay, so that means this is also an equipotential surface. All right. Now, since you are considering the distance between these two surfaces, and if you make these two surfaces very close to each other, that means what you're doing, you are actually decreasing this distance dr. So what we will see that the electric field between these two planes, and this is a very strong electric field. This is what we can make out from this point. Another point, if you increase the distance, that means this dr, what will happen? This electric field value will decrease. Clear? So that means when you are increasing the distance between two equipotential surfaces, so in that case, your electric field strength will be very small. That means it will actually tell a very weak field. Okay. So this is what we can make out from this third point. That means equipotential surface are very closer for strong field, and equipotential surface are very far apart for weak field. Okay, so this is my third point. Now our last point, it says that no two equipotential surfaces can intersect each other. Obviously, let's say that you are having an equipotential surface whose potential is VA, and let's say that you are having another equipotential surface whose potential is UB. So if you see this this point of intersection, okay, this is my point of intersection. So at this point, you will have two potential values, right? But which is not possible. So that is why at the point of intersection, okay, since at the point of intersection, potential, we have two potential values, which is not possible. It is not possible. That is why no two equipotential surfaces intersect each other. So these are the 5 properties of equipotential surfaces. So this is our next topic, electric potential energy. we had studied different types of potential energy. We had studied about gravitational potential energy. We had studied about elastic potential energy. So in all those types of potential energy, we have understood or we have expressed in such a way that we first basically find work done. Okay, this is the physical quantity which we find, and that work done performed by any body. Okay, so that work is actually stored as potential energy, but in various different forms. Okay, so here also we will be deriving or we'll be finding a certain work value, and that work performed by a charge, since we are discussing it for electric potential energy. So that work has to be performed by a certain charge, certain set of charges. So that work is actually stored as electric potential energy by those set of charges. Okay, so let's just understand, how that work is being performed by those charges. So to understand that, first we will assume that certain charge. Let's say that you are having Q1, and let's say that you are having another charge Q2. Now these two charges, they are assumed that they are very far away from each other. And when we say far away, I have assumed that they're at infinite position away from each other. They are infinite distance away from each other. Okay, so when they are at infinite distance away from each other, so one charge, none of them is having the effect of the other. Okay, he's not going to feel the effect of this charge Q1, and Q1 is also not going to feel the effect of this charge Q2. Okay, as they're very infinite distance apart, and they are located at their own distinct position. For such case, there is no work done value. Okay, for this two charge bodies, and Q1 and Q2, there is no work done. And since there is no work done by these two charges Q1 and Q2, so the potential energy for such set of charges, okay, which are very infinite distance away, the potential energy value is 0. But what if I bring this charge Q1 from infinity to a certain point? Let's say that that point is A, and if you bring your charge Q2 to another point, let's say B, obviously that you are performing a certain work there, you are having a certain work, because both these charges are brought from infinity to a point, right? And the more closer you want your charges to move, okay, there is going to be more force of repulsion in between Q1 and Q2. Okay, because both of them I have assumed that they are positive, they are same sign charges. So that's why when you move those charges more closer to each other, so you will have more force of repulsion in between, and the work done performed by those two charges Q1 and Q2 will be against that force of repulsion. Okay, you can make this as the point that work done in bringing the charges Q1 and Q2 from infinity to their respective positions. Is against the force of repulsion. Okay, is against the force of repulsion. Okay. So this work done performed by this charge Q1 and Q2, this work done is stored as electric potential energy. Okay, and this work done is possessed by this system of charge. Okay, so this work done is possessed by this system of charge. Okay. That is Q1 and Q2. Okay. Then the more you try to make them move closer toward each other, that you will have more work done value. Hence, you will have more electric potential energy value. Okay. So we have understood that this work done is actually the main source, or you can say the origin of the electric potential energy between the charges Q1 and Q2. Okay, so that means if I want to define that what is my electric potential energy, so we can define it in this way, that the electric potential energy of a system of a point charge may be defined as the amount of work done in assembling the charge at their location by bringing in from infinity. Okay, so in that way we can define it. Right? So you can make this as a point that potential energy, electric potential potential energy is possessed by a charge, electric potential energy is possessed by a charge is the amount of work done in bringing the charge from infinity to that point. So in that way we can define our electric potential energy. So now we will derive the expression of electric potential energy step by step. We are going to do. Okay, we are going to find out electric potential energy for a two-charge system, and then we are going to find out electric potential energy for a three-charge system. That we are going to do, and then we are going to understand a separate special case, that what should be the electric potential energy. If I place those charges in an electric field, and if I place it in the absence of an electric field. All these cases we are going to deal with. Okay, so our first point is to find out electric potential energy for a system of two charge. Okay, so for that, what we are going to perform it in a different way. So what we will do, first we will bring our charge, one of the charges, let's say Q1 and Q2. But before going into that, we just state a certain point that we know that what is potential, the electric potential is nothing but W by Q. And since we are deriving electric potential energy, so that means we are actually finding out our work done value, which is nothing but charge, that charge is moving multiplied by the potential value at that point. So we are going to use this expression here. So we had stated our initial points. Now using this initial concepts, we are going to find out our potential energy. So first what we will do, if you see this region, we will consider a certain region. This is my any space, and now in this space you are having no charge. Now since you are having no charge in this space, so that means at every point you are having no potential. So that means the potential at every point inside this box is 0. But if I bring a charge Q1, let's just say that you are having now a charge Q1. Initially, you didn't have this charge Q1, and because of which you didn't have any potential at every point inside this box. Now, since you have placed a charge Q1, because of this charge Q1, you will have now potential values, electric potential values at every point now. Okay. So since we are having potential now, so we will assume certain points. Let's just say that this is one of the points. Let's say A. Okay. So the potential at A, let's just say that it is nothing but K Q, let's say Q1, Q1 by R. Okay. This distance here, let's just assume that this distance is R. Okay. So now what we do, we will bring another charge, let's say Q2. And he's coming from infinity. He is now at infinity. And he is moving from infinity to this point A. Obviously, since he is coming from infinity to this point A, so he is going to perform certain work. And that entire work will be stored as potential energy for this charge Q2. So the charge Q2, which is at infinity, is moving towards point A, where potential, that means at A, okay, at A is V suffix. Okay, so therefore, work done. Work done by whom? Work done by Q2, because he is moving, right? He is moving from infinity to point A. So work done by Q2 will be how much? We are going to use this formula. Okay, so in place of Q naught, now we will place Q2 multiplied by the potential at point A, right? Because this here, this V value is nothing but the potential at a point to which this Q naught is brought. Now, since at point A we are having this VA potential, which is nothing but KQ by R. Right? So we are going to use this potential value at A. Okay. So if you replace this VA value, we will see that it is nothing but K Q1 by R. Right? Let's just say that this is W. Now, since we have index 1 and 2, so instead of writing just W, we will put certain index Q1, 2. And this distance we will represent it by R12, because this is the distance between charge Q1 and Q2. So that is why we are using this index R12. So everywhere you replace it by this index R12. Okay. So this is the work done in bringing the charge Q2 from infinity to point A. This work done, now this work done is only stored as potential energy. Okay, so therefore, work done W12 is stored as electric potential energy, and we represent it by U. Okay, so this U is nothing but K Q1 Q2 by R1. Okay, so this is the amount of potential energy stored between a system of two charges. All right. Now, if I assume it a three charge system, then what should be the expression of the electric potential energy that we will derive? Okay, this was for two charge system. Now we will assume it for a three charge system. Okay. Second point, third point, second point. So electric potential energy, electric potential energy for a system of three charge, right? So similarly, the way we had proceeded for the earlier case, that's in that same way only we are going to proceed. So we will assume a certain space. Okay. Now you don't have any charge. This is the initial case. You don't allow any charge in this case. So at every point you don't have any potential. Okay. Now if you bring a charge Q1, now this charge Q1, he is not going to experience any potential. He itself can behave as a source, but he is not going to experience any potential because you don't have any external other source except Q1. Okay, so work done by this Q1 charge will be 0. Why? Because even if you are placing this charge Q1 here, so at this point Q1, he has to experience a potential, and that potential will be due to some other source. Since he itself is a source now, and you don't have any other sources except Q1, that is why there is no potential at this point. That is why work done by this Q1 charge will be 0. Now he is behaving like a source charge. He will be generating an electric field. And because of this Q1 charge, you will have different potential values at different points. So now what I will do, I will bring another charge, let's say Q2, and it is placed somewhere here. Let's say this point is A, and since we are having indexes 1 and 2, so we will assume that this distance between 1 and 2, let's just say that it is R1. Okay, so we will have potential at A due to Q1, which is nothing but K Q1 by R12. This is the potential at A due to Q1, and at this point A only you have brought your charge Q2. So that means since you have brought this charge Q2, he is performing certain work, and that work is only stored at this point A. So therefore, work done by charge Q2 in moving from infinity to point A. So that is nothing but, it is going to be nothing but Q2 multiplied by VA. So that is my second work done. either whether you write W2 or you can write W bracket Q2. That way also you can write. If you replace your VA value, so it will be nothing but K Q1 by R12. So W Q2, you will have a value K Q1 Q2 by R12. So this is the work done. Okay. But since we are doing it for a system of three charge, for a system of three charge. Okay. So that means we have to bring another charge. Okay, let's say Q3. This is my another third charge, which is brought in this space. Now Q3 will experience a potential due to both the charges Q1 and Q2. That means if I bring this charge Q3, let's say to a point B, so that means this point B will have potential due to charge Q1 and also due to charge Q2. And if I assume the distance between these two is, let's say, R13, distance between these two, let's say it is, R23. Okay, so you will have a potential at B due to charge Q1 and also due to charge Q2, because of which you will have work done due to both these charges Q1 and Q2. So separately we find, therefore, work done by charge Q3 in moving from infinity to B. Who is performing this work? Q3. So let's just say that it is Q3. And since you are having potential at B, which is nothing but the addition of potential due to Q1 and Q2, that's why you write it V1 plus V2. V1 is the potential due to Q1 at B. V2 is the potential due to Q2 at B. So you replace this V1 and V2 value. So again, it is going to be Q1 R13 plus K Q2 R23. Okay, so it is going to be Q3. All right, so this is the work done by whom? Q3. And if we distribute it, so you get something like this: K Q1 Q3 by R13 plus K Q1, Q2 Q3 by R23. Okay, so you have two work done values. Okay, you are having this equation 1 and you can give this equation 2. You are having two work done value. Now when you find your net work done, you just add all these three. Oh, sorry. So you are having three equations. This is my first equation. This is my second equation. And this is my third equation. We are having three work done values. Okay, so you are going to add all these three work done values in order to find electric potential energy for a system of three charge. You're going to add all these three work done values. Okay. So net work done be work done due to charge Q1 plus work done due to charge Q2 plus work done due to charge Q3. Work done due to charge Q1 will be 0. Due to charge Q2 will be K Q1 Q2 by R12. And due to Q3, it is nothing but K Q1 Q3 by R13 plus K Q2 Q3 by R23. So this is my work net. So it is nothing but K Q1 Q2 by R12 plus K Q2 Q3 by R23 plus K Q1 Q3 by R13. This is my net work done. So therefore, as I already said that you find electric potential due to the work done value which is stored between the charges. So this is my work done value which is stored. So this work done, therefore the work done is stored as electric potential energy. And how do we represent that? We always represent electric potential energy as U. So in that way we find the expression which is nothing but K Q1 Q2 by R12 plus K Q2 Q3 by R23 K Q1 Q3 by R13. So this is the amount of potential energy stored by the system of charges. What is the system? Q1 Q1 Q2 Q3. Distance between them R12, distance between them R13, distance between them R23. So you must have observed that when we derive potential energy, we see that how many pair of charges we have for any system. Okay. So for those pair of charges, we find out our potential energy, electric potential energy. Let's just say that if I give you a 4-charge system, let's say that you're having Q1, Q2, Q3, Q4. You're having 4-charge system. So here you will have 6 pairs. This is one pair Q1, Q2. This is another pair Q1, Q1, Q2. This is the other pair Q2, Q3. This is the other pair Q3, Q4, and this is the 4th pair Q1, Q4. 5th pair Q2, Q4. 6th pair Q1, Q3. Okay, so you're having 6 pairs in such arrangements. That means when you will find potential energy, you will have 6 different terms. Okay, 6 different terms you have to find it out. That means you will have potential energy 1, 2, potential energy 2, 3, potential energy 3, 4, potential energy 4, 1, potential energy 2, 4, potential energy 1, 3. So you will have these 6 terms. And when you replace all these 6 terms, then only you will be able to find what is my net potential energy for such system of charges. Okay, but remember, this potential energy we are able to find is when you are not applying any external electric field. See, here we have not applied any external electric field, so that means this is the case in the absence of external electric field. We have not assumed any such field, but we are going to derive an equation where we have an external electric field. Because of that external electric field, the potential energy value gets they gets little modified. Okay. So this is our another topic where we will find out expression of potential energy in external electric field. Okay. So before going into finding out potential energy in external electric field, first we will write down the expression. In what was the potential energy expression in absence of external electric field. So in absence of external electric field. So we did that for 2 charge system and for 3 charge system. Okay. So number 1, 2 charge system. So for 2 charge system, our potential energy was K Q1 Q2 by R12. This was our expression of potential energy for a 2 charge system. If I write the expression for 3 charge system, okay, for a 3 charge system, so our potential energy expression was K Q1 Q2 by R12 plus K Q2 Q3 by R23 plus K Q1 Q3 by R13. This was the expression for potential energy for a system of charge in absence of external electric field. Okay, but what if we assume that you are having a certain electric field? Okay, so this is our second case in presence of external electric field. So when you allow an external electric field, certain extra work done or extra work done value comes across. Okay, so due to the presence of external electric field, at every point you will have certain different potential. Okay, and those potentials will be due to this electric field. Now this electric field can be from a different source. Okay, so that source will be mentioned in our question, and basically due to those outside source which is generating this field, and this field is applied on system of charges, you will have certain extra potential. So for 2 charge system, okay, for a 2 charge system, our potential energy equation was K Q1 Q2 by R12, right? How was our diagram? Now this was Q1 and this was Q2, and both of them were placed at R12 distance. Now since Q1 and Q2 were located at a different position, so at this position, due to this external electric field, we'll have a potential V1, and due to this external electric field, we'll have another potential at charge Q2. So due to this potential Q1, our extra work done will be done, and that work done will be nothing but Q1 V1, and due to this potential V2, you will have another extra work done, which is nothing but Q2 V2. All right, but here you didn't have such case. Why? Because let's say that if you are having any region and here there is no field there. So if I consider 2 points here, A and B, so there is no potential because you are not having any field there. So initially the potential value was 0 for A, and for potential value for B was also 0. But in this case, even if the charge was not placed earlier, okay, but still then you will have extra potential V1 at this point. Let's say now this point is A, and you will have extra potential at point B, and that potential is V2. So because of this V1 and V2, which is due to this field, external field, you will have extra work done, which is Q1 V1, and extra work done, which is Q2 V2. Okay, so this is the net potential energy for a system of charge in external electric field. Okay, the same thing we can apply for three charge system. So for three charge system, our potential energy expression was this only. Okay, K Q1 Q2 by R12 K Q2 Q3 by R23 plus K Q1 Q3 by R13. And this was the potential energy for three charge system. But this was the equation when you didn't have any external electric field. But in this case, we are assuming that you are having an external electric field. Obviously, so this Q1, Q2, Q3, okay. So this Q1, Q2, Q3 will be located at three different positions. So in presence of external electric field, those three positions will have different potential value. Let's say for Q1 it is V1, for Q2 it is V2, for Q3 it is V3. You will have different potential. And why you are having these three different potentials? This is due to these external electric field. Okay, so you will have extra work done due to the potential V1, and which is nothing but Q1 V1. Again, you will have extra potential due to this extra work done due to this potential V2, which is nothing but Q2 V2. And similarly, you will have extra work done due to this potential V3, Q3 V3. So this is my net work done or net potential energy for a system of charge in external electric field. Okay. So all you remember one thing, that if you don't have an external electric field, so your potential energy will be only due to the system of charges. But if you allow an external electric field, so the net potential energy will be due to this system of charges which is placed at different position, and also due to the electric field which is applied on those charges, which will give potential V1 and V2. So this combination of these two different types of work done will give you the net potential energy for a system of charge. Any system you can consider, for two charge system, three charge system, for four charge system. So we need to be very much careful to understand the question, whether in our question it is mentioned that the field is applied or not. If you don't have any field, external field, so our expression for finding out potential energy will be this two. Okay, this is how we find it out. But if in our question a field is given to a system of charge, then the expression for finding out potential energy will be in this form. Okay. Okay, so this is our another topic. Here we will understand that if you place a dipole, okay, in a uniform electric field, that then how much potential energy is stored by this dipole. So that part we will understand. Okay. So in charges and field, we have understood that if you place a dipole in any electric field, there were two cases. In one case, we used to place a dipole in uniform electric field, and in another case, we place a dipole in non-uniform electric field. Okay. So in uniform electric field, we have understood that that dipole in uniform electric field, there is no net force acting on that particular dipole. The net force acting on the dipole becomes zero; it gets cancelled. Okay. Let's just say this is my dipole, and let's just say that this is my any electric field. Okay, this is my any electric field which is uniformly directed in this direction. Okay, So obviously what will happen that this charge minus q is going to experience a force in this direction, which is minus QE, and this charge is going to experience a force in this direction, which is plus QE. So that's why your net force acting on the dipole becomes zero, because both these forces gets cancelled. Okay. So what happens that in uniform electric field, the dipole does not have or is not having any transitory motion. It means he cannot move in the straight line path. But yes, due to this oppositely directed force which is acting on this dipole, this dipole is actually going to rotate about its axis. That means about this point O. As you can see here, about this point O, this dipole is going to rotate. And because of this rotational motion, the dipole is going to have a certain torque value. Okay. So that torque we represent it by tau, and we had expressed it as something like this: P sine theta, where P is my dipole moment. Okay, so P is my dipole moment, and what is that? What is dipole moment? So it is nothing but product of the charge with the separation between the dipoles. Now in this case, the separation between the charges in a dipole. Now in this case, the separation between the charge is twice A, okay, and the dipole moment, okay, is directed from negative to positive. These are the preliminary ideas or the preliminary concepts which is related to any dipole. Okay. Now, since we are considering the case where this dipole is placed in a uniform electric field, so obviously, we are going to consider this dot expression, because he is not having any transitory motion. He is having only rotational motion, and we will be finding out again, since we are finding out potential energy. So obviously, we have to find work done by this dipole. So we are actually going to find out work done with respect to rotational motion. So that work done with respect to rotational motion will actually provide potential energy to this electric dipole. Okay. So step by step we are going to find it out. So we had already stated that in a uniform electric field, the dipole is having rotational motion. Okay. And the torque, okay, acting on the dipole in uniform electric field is given by tau equals to E sine theta. You can give this equation 1. Okay, this is the value of torque which is acting on the dipole. Then let's say that d theta, the angle of rotation. Since your dipole is rotating, so when when your dipole rotates, so there is certain change in angle. Even though there is no change in its position, you don't have transitory motion. But since he is rotating, so you will have change in the angle value. And what is this angle? Angle between dipole moment and this electric field. As you can see here, this is that angle theta. So let's just say that you consider any d theta angle, okay, and we will be finding out work done for this d theta angle of rotation. Okay, so therefore work done dw. This is my work done, okay, in rotating the dipole by angle d theta. Okay, so we have understood earlier that work done is nothing but force into a displacement. So in that way only we are going to do. But in this case, that force into displacement will come across only for transitory motion. But in this case, we are considering a rotational motion. So in the place of force, torque will be taking over, okay, because in rotational motion the physical quantity which replaces the force um, part is the torque here, the torque experienced by the dipole, and that torque is multiplied by the displacement, but in this case that displacement is my angular displacement. As you can see here, this theta is my angular displacement, so that angle is theta. So theta is nothing but my angular displacement. Okay. So we will replace all this torque expression. What is that? E sine theta multiplied by d theta. This is my work done in rotating the angle by angle d theta. Okay. Now what we will do, we will be considering two different angles between which your dipole is rotating in a uniform electric field, and those two limiting values of theta, considering those two limiting values of theta, we will find out our work done value. So let's say that if theta 1 is the initial angle, uh, between P, dipole moment, and electric field, and theta 2 is the final angle. Theta 2 is the final angle uh, to which the dipole is oriented. To which the dipole is oriented. So that means initially this dipole was making certain angle theta 1, which I have mentioned it here, theta 1 with this electric field. Now since once you give him certain electric field, so what will happen, that dipole is going to orient, and that means he is going to rotate, and let's say that after rotating he attains an angle theta 2 with respect to angle with respect to electric field E. So how much amount of work has been done in rotating the dipole from angle theta 1 to theta 2? So that only will be our net work done. Okay. So therefore, our net work done will be nothing but the integration of dw, and we express this dw as nothing but P sine theta d theta. So remember, we had assumed that initial value of theta was theta 1 and the final value was theta 2. So you replace it by theta 1 and theta 2 as the limiting values. So P and E, both of them are constant, so they come out from the integration part. You are having only theta 1 here and theta 2 here, sine theta d theta. Okay, so you do the integration, so you get how much? Integration of sine theta is nothing but minus of cos theta, theta 1 by theta 1 and theta 2, upper limit and lower limit. So when you replace this upper limit and lower limit in this cos theta function, so you get something cos theta 1 minus cos theta. Okay, because you have a minus sign here, so that minus sign is getting calculated here, and finally you get the expression cos theta 1 minus cos theta 2. So this is the amount of work done, okay, in rotating the dipole from angle theta 1 to theta 2. Now let's just assume that initially, okay, initially theta 1 value is 90 degree. This is our assumption, huh? So that means when we say 90 degree, so that means your dipole initially it was perpendicular to electric field. Okay. So and let's say that your final value, okay, finally, let's say when you are having this dipole in electric field, and when it rotates, let's say that your final value, which was theta, let's say it is theta 2, let's say it is theta. Okay, so in that case, if you replace your work done value, and if you replace theta 1 by 90 degrees, so you will get cos 90, which becomes 0. And if you replace theta 2 by theta, you get a minus cos theta. So you directly replace this part, which is nothing but minus cos theta. So finally it gives you minus p cos theta. Okay, so remember that this is the case when your dipole initially was in perpendicular position to electric field, and then he is rotating to a certain angle theta. For such case, now what should be your work done expression? There is nothing but minus P cos theta. Okay, so this is the amount of work done. Okay, work it has been done in rotating the dipole from certain initial angle to certain final angle. Okay, so this work done is being stored as electric potential energy. Okay, so therefore the work done is nothing but minus Pe cos theta. Okay, minus Pe cos theta. So this work done, it is stored as electric potential energy in uniform electric field. Okay, so this is the amount of electric potential energy which is stored in a dipole. You can modify this statement more properly. It is stored as electric potential energy in dipole. That is a more proper. In stored as electric potential energy in dipole, okay, when it is placed in uniform electric field. This will be more proper. Okay. So here we will understand what are the special cases of a dipole when you place it in a uniform electric field. Okay. So previous to this topic, we have studied that the potential energy which is related to any dipole in a uniform electric field is around minus Pe cos theta. So we are going to take this equation in consideration, and then we are going to find out what are those special cases. So out of those, we have basically three special cases, and out of those special cases, the very first case is position of stable equilibrium.
position of stable equilibrium. So let's just understand, what does this stable equilibrium means. So here what we do is that when we consider this equation minus PE cos theta, so we make this angle theta 0 degree. Okay, we take this theta as 0 degree, and when you take theta 0, then if we find potential energy, so it comes out to be minus PE. Now this minus PE, it is nothing but the minimum value of potential energy. Minimum value of potential energy. Potential energy. So this condition, the point at which you find your potential energy minimum, so this condition is known as position of stable equilibrium. So in boards or in any exam, it is asked that what is the condition at which your dipole will be at stable position in uniform electric field. So your answer should be like this, that when your potential energy is minimum, that means this minus PE, and the potential energy will have minimum value at angle 0 degree. So this condition is known as position of stable equilibrium. Okay. So this is our first special case. The second special case is position of unstable equilibrium. Unstable equilibrium. Here what we do, again we consider this equation minus PE cos theta, and we make this angle theta as 180 degree.